I want to thank our audience for joining, and I would like to introduce today's speaker. Dr. Alan Hubbard is a professor of biostatistics at UC Berkeley. His research focuses on the application of statistics to population studies with particular expertise in semi-parametric models and the use of machine learning and causal inference, as well as applications in high-dimensional biology. Today, Dr. Hubbard is going to talk to us about cross-validated targeted maximum likelihood estimation, or CV-TMLE. So, Alan, thank you for joining us. And now I will mute myself and turn the presentation over to you.
Great, thank you so much. First of all, thank you so much, Susan, for the invitation. And it's an honor to be speaking to you all. As Susan said, I'm a professor of biostatistics at Berkeley and have played around in the targeted learning, or more fumbled around in the targeted learning framework since the original TMLE paper came out in 2006. I wouldn't say I'm a qualified theoretician, but I'm interested in how theory predicts the performance of estimators and how it can be used to lead to more robust statistical machines. And I hope to convey some of that through this talk. This talk is narrow in focus, so it's not about causal inference so much, although we'll talk about estimating causal parameters. It's mainly about the estimation part of that and the inference part. Today I will focus on an augmentation of TMLE called CV, or cross-validated TMLE. And at the end, I'll show we have a preliminary large-scale realistic simulation study using existing data sets to look at the relative performance of these estimators. And I'll show those results. Because it's a realistic simulation, the results are not incredibly clear, but I think they give us some insights into these various estimators. This work is done in collaboration with a group of people at Berkeley mainly, and at Gates Foundation, which has funded this overall effort, which includes deriving a new kind of software framework called TLVerse and applying it to their data, which consists mainly of childhood development studies that we've looked at in developing countries. I'll go over some quick background. Well, actually not that quick, but I'll go over TMLE. It'll be, I'm sure, a review for many of you, but just to create the context to discuss CV-TMLE. And I'll talk some heuristics about the theory, that why CV-TMLE is a potential improvement to the standard TMLE. I'll explain what the difference, of course, before I get there. And then after discussing these results, I'll talk a little bit about how one, even if none of the estimators perform well, is there a way of redefining the parameter? I have to give the caveat, none of this is original work except for the simulations. This is work that's been done by many people, Susan included. So this is a schematic of the targeted learning roadmap, and I'll go over some details of the individual sections as we continue. There are other, of course, methods to incorporate machine learning in the estimation of causal quantities that utilize machine learning, like estimating equation approaches like IPTW or the augmented version of that, and we will look at relative performance of those estimators lately. So but I'm mainly concentrating on the targeted learning part of that. The great value, I'm sure you've heard if you've been to other talks, is that you can use highly adaptive machine learning algorithms and still derive inference for the resulting quantities. So you can get legitimate confidence intervals, p-values, et cetera, even though highly data adaptive methods are used. Let me just go to a more explicit list of these. So, here's the series of steps that are listed in the roadmap. You have just the observed data that you have to describe its distribution, the study, whether the study is an IID sample or a bias sample, specify the statistical model. That's where much of targeted learning comes in, because we want to estimate things in very big models where we don't want to make strong parametric assumptions that are not supported. Define the statistical inquiry. So that's the causal inference part. Usually, or at least often, there's a causal quantity of interest, like the difference in mean outcomes. If I intervene on some variable, like give treatment, everybody experiences treatment, gets an outcome, and then with an identical population have no treatment and compare those outcomes. So we're not going to go too much over identifiability, or essentially none at all. We're going to just jump to the estimand that results, which is a function of the data journey distribution, and go from there. Finally, you have now a math problem, so you have to construct an estimator in that model. Of course, a lot of work has been done by Jamie Robbins and Mark Vanderlyn and others in order to do that in an asymptotically efficient way. And then, of course, use some of the byproducts of the estimation procedure, specifically the influence function or curve, to obtain inference. Now, I'm really just talking about essentially 4 and 5 in this talk, and not so much about 1, 2, and 3. So just to go a little bit more detail of these steps, describe the observed data. This is the type of models that causal models we're looking at, where we have pre-treatment covariates. We have an A. A few of the studies that we'll look at, they're randomized. Other ones are from purely observational studies. And outcome, in our case, it's a continuous outcome, has to do with child development. So height for age Z-score. Our main A of interest, what we'll look at later, will be nutritional interventions. Again, sometimes they're randomized to subjects. Sometimes it's a large observational study where they just report whether they receive them. And again, these studies are mainly in Asia and Africa. It's part of an ongoing applied research effort in collaboration with Gates to look at large-scale meta-analyses to see what things are best at explaining and predicting failure of growth, things like wasting and stunting. It's just the propaganda slide for trying to motivate targeted learning. Standard approach assumes a very small model represented by this little blue cloud. And of course, unless your actual data generating distribution, P0, resides in that small space, estimation will be biased if you do parametric types of analyses, parametric regressions, etc. And the idea is that you want to estimate them in a really big, realistic model. Often this is non-parametric or close to it, so we assume very little. Maybe we assume bounds on the outcome that we happen to know, or other types of things. We're working on methods that are able to incorporate other kinds of constraints on the likelihood, like if you have previous estimates of causal effects from randomized trials that you believe are true, or you have some interval, you can incorporate that as well. That's for future. It's very interesting work, very challenging, and at this point, not readily available. And so the idea is targeted learning is able to estimate these parameters of interest in a realistic, very big model, non-parametrical model, and in that case, you can guarantee in the limit they're unbiased because the true distribution lies in the big space. Just to give a toy example of how we might demonstrate this, this is just data from manufactured data from a study that has an outcome. That's on the y-axis. It has one covariate, that's this one, and then it has two different levels of treatment. A is 0, purple, and A is 1, green, and this shows the data and some fit, the actual true model fit through that data. So we'll just look at that just sort of to see how it works in practice. This will be the estimate that I'm focusing on. This is an estimate that identifies with assumptions the average treatment effect, that is the difference in the mean outcome if everyone's treated, gets the nutritional intervention in our case, versus if they don't get the nutritional intervention. As always, this will require assumptions, this identification, such that W has all the relevant confounders, a consistency assumption related to dependence of the counterfactuals. We're assuming they're independent. And one very important assumption that factors largely in this talk is the assumption of positivity, which is, in my experience doing, at this point, dozens of data analyses using targeted learning. And this is often a very problematic assumption, which just assumes that there's enough experimentation in the data that for every subgroup of people defined by your W's, you have enough experimentation with regard to treatment. And I'll talk at the end a little bit, the methods we're talking about somewhat ameliorate the impact of this, but at the end there's ways to avoid the violation of the assumption by just changing the definition of the parameter. And so this is the basic framework. Then that's the parameter we're going to talk about estimating when we contrast targeted learning to the cross-validated version. So this shows just a simple contrast of, again, it's a toy example, so it's not meant to portray what realistically would happen in practice, but you have the left side, the standard approach, let's say assuming a parametric model with main terms, A and W, and some kind of error. The estimated coefficients, well, they're not necessarily biased. That's depends on what you're trying to estimate. You're trying to estimate the projection of this function onto a different space, like a non-parametric space. They may be unbiased for that projection, but they're not getting you at what you wanted to get at, which is this causal quantity. And they don't automatically detect heterogeneous treatment effects. We're not talking too much about that here, but and then on the right, you can see the fits. Of course, you have two main term effects, main term, and you get two flat lines, of course, for the things because you're going through these kind of quadratic curves. And then we have, in contrast, a super learner fit for these two groups. You can see, and we as well have. This is jumping a little ahead, but the targeted learning update and its fit to the data, obviously it's much closer given it's using machine learning and making no particular assumptions and has enough flexibility they can pick up these nonlinear trends. But the impact is something like this. Here's the estimated treatment effect, which can just be the coefficient in that linear model. That would be an estimate of the average treatment effect if the model was correct. And you can see the, confidence interval excludes the truth, and it's obviously biased as we set it up to be. The super learner here, you can see does not have a confidence interval. This is not a asymptotically linear estimator, meaning there's no associated central limit theorem for deriving confidence intervals, and it has no predictable sampling distribution. It's one of the reasons why you need an additional step like TMLE, which removes bias and smooths the estimator so it performs like a asymptotic linear estimator, like an IID sum of random variables, and therefore you can derive both standard error from the influence curve, which you may have seen if you've seen previous talks, and a confidence interval. And so this just gives the basic generic setup for TMLE in a very qualitative kind of way. Now, why we're doing this research, and particularly the specific software development we're doing with Gates, is we really want to move towards statistical machines ultimately, where you could, in theory, take all the constraints on the likelihood that you happen to know, and these can include bounds on the random variables, constraints on having to make certain parameters equal to values, whatever it happens to be, and put those in. You can even, we do have a package that's not unique, but it will take causal graphs in, and you can identify nodes you're interested in, identify pathways to the outcome you want to estimate, and it will automatically generate the estimand from that and go forward. And then after you put in all these constraints, what you know about it, the design, what you know about the causal model, you press a button, and it's guaranteed to optimize estimation given your particular sample size, your peculiarities of the data-driven distribution, et cetera. It could also return information that says you can't estimate this quantity, because that can often occur, particularly with severe positivity. You just don't have the information to estimate it. That's something that, of course, parametric methods will often obscure because they easily extrapolate. So there's no obvious warning to you that something's going wrong. And these estimators that we're discussing today can tend to break down by blowing up if, in fact, the lack of experimentation is really problematic. And they can use data adaptive methods that automatically account for sample size and the way they're selected, smoothness of the data during distribution, et cetera, and return the estimates with inference that you want. And this may even be choosing between estimators. We haven't looked at that too much, but that would be another way of building in this flexibility. So we're not at this stage, of course, but the ultimate goal would be to create something where it requires the user to concentrate on what they really know about the data-driven distribution, any constraints, any previous information, and what they know about the causal model, and then not have to get into the details of the model selection part and all the other inner workings of the black box that will return the estimates. And of course, you'd ultimately want it to return diagnostics of some kind, like regressions do, things that relate to positivity or relate to other aspects that may provide information on how to interpret what you get in the end. So I would say this is our long-term goal of many people working in this field around that. We're getting, I think, somewhat closer, but we're not there yet, of course. But it's just a little schematic showing this. Obviously, it's important to have asymptotic theory. It kind of creates a way of distinguishing among estimators and driving something that could be asymptotically efficient in the limit, and it gives you justification for inference, et cetera. But theory is not always available for optimizing its finite sample performance when you get in this area, where things can start to break down. So asymptotopia doesn't necessarily predict what happens in finite sample. Of course, it is somewhat predictive, and that's why we use it. But we need lots of work in this realm here. And this is the kind of work that people like Susan Gruber have contributed so much to by doing things like modifying how you select certain models in order to get better, more robust performance, to avoid this kind of blowing up and breakdown, things like collaborative targeted maximum likelihood. And I'm not talking too much about that today. I'll explain why in a little bit, but that's another great contributor, and one that I've have worked on in showing its performance can be much, much superior to things that do not have this augmentation in order to avoid severe positivity problems. So one way to look at it is do realistic simulations. I'll describe those in more detail in a bit, but that is simulations that are closely related to actual data that you have. And we're trying to build up a sort of library of different kinds of data sources and look at the relative performance. Obviously, competitions are very important, and Susan as well has been integral to creating these kind of competitions where you have data generated from complex simulations that the user is unaware of mechanics, and people try to submit their results, and of course the proofs in the pudding, how well they actually do in practice, both on mean squared error, for instance, and also things like coverage of somewhat more importantly, how well confidence coverage performs. Is it close to the nominal rate? And so this I consider this work that we're presenting a small part of that, a small part of that effort, which has been ongoing since the day that these methods were proposed. All right, so now to get into more gruesome detail about the underlying estimators we're going to talk about and the specific parameter. So I'll do a little light theory. I'm not really capable of doing super deep theory, so I hope to give some heuristics for why this augmentation is important and why it leads to more robustness, and how it might be combined with other methods to give something that gets closer to a machine. So the first step in estimating the average treatment effect, let's say, is you need some initial estimates of the relevant parts of the data during distribution. You know, one of them obvious from looking at the estimate is you need an estimate of the prediction model of Y given the covariates, both the treatment A and the confounders W. And for these, we generally emphasize superlearner, and for various theoretical and practical reasons. This is a complicated diagram that shows exactly how the algorithm works, but it's a clever use of cross-validation and ensemble learning. It's an example of ensemble learning, where you fit a sequence of algorithms on training samples, evaluate them on the validation samples, and in the simplest form, the discrete superlearner, you choose the algorithm that performs best on this independent validation samples. And the theory shows that if you do, or I should add, you can also get, like down here, a weighted combination of these as well, either through logistic form, or you could do it for linear form if that's, you have a continuous outcome. And the theory is important here because it predicts that you almost can't try too many learners, that if you have, let's say, a sample size of n, then you don't really get kind of overfitting that would come from just sheer luck until you're talking about an order of n squared number of things you add. So the theory says you should add a lot of learners, things that are smooth, things that are simple, maybe even just an intercept term, all the way to very complex, then flexible random forests, XGBoost, deep neural nets, whatever it happens to be. And a lot of this talk is about, for TMLE, it has one constraint that says your learners can't be too adaptive. And we'll talk more about that. And that's where CV-TMLE comes in, because you can't overfit. Even though you're doing a great job in the prediction model, it may not be so good for estimating your target quantity. I think I've got most of this so far. It's the basic theory shows that it's hard to come up with a gold standard for machine learning, and that there's no universally optimal machine learning algorithm for every sample size and every data drain distribution, but you can at least create a gold standard, which is the best one that you have in your library. And so, which is another reason to create a big library, because you're more likely to capture one that's closest to the truth. So you can show that in terms of risk or in terms of fit, that the superlearner performs asymptotically as well as the oracle. That is the one you would choose if you actually knew the data during distribution. So, I mean, that's like fitting all the regressions on the data and then evaluating them on some infinite sample size, say, and superlearner will be equivalent to choosing the one that does the best on the infinite sample size and limit. And of course, you add greater flexibility by the weighted combinations. Of course, the more flexible you make that stage, the last stage of superlearner is just think of it as a simple parametric regression. And that's done so you don't overfit in that last stage. You have all these predictions that are in the scale of the outcome, and you want to get something where you don't really have to count for that part of the estimation in terms of overfitting. And so, but you can get much better performance by having a weighted combination. It just increases the flexibility of the algorithm. And because can be represented as a simple parametric form, you don't have that problem with overfitting. So basically, more competitors, better performance. Of course, in practice, sometimes the data is so noisy that, the simplest things tend to do the best, or maybe it's truly smooth, and that as well. So, things in theory don't always look so impressive in practice, but it's always good to start with something should be optimal. This is done by Eric Pauly, done years ago, just taking a bunch of studies and performing kind of cross-validated analysis. So it's a within study measure performance where they cross-validate all these procedures, including superlearner and discrete superlearning, and it's all relative. So the relative mean squared error is relative to GLM. That's why there's just a little dot here. The red represents the average performance across all these studies. It's in the tens. It's not a huge number. And you see the kind of pattern that we often see, that superlearner does generally pretty well. It does about as well or better than the best performing candidate that's included in it. And even though some things can perform quite well, like random forest, they sometimes screw up. And so you never know this going in. Superlearner is just like hedging your bets to avoid the pitfalls that can happen from any single algorithm. And again, if you ever find an algorithm that's better than superlearner, then you should just add it to it. So it almost can't be beat by definition. So more details to try to explain why CV superlearner might be an improvement. And we'll just start with defining a simple substitution estimator. We have this sort of standard, at least notation in Berkeley. I know this varies elsewhere, and that's always annoying. So I apologize, but we have independent observations of O on across some set of subjects, where W is the confounders, A is the treatment, again, binary, we're going to assume now, and Y is the outcome. We'll assume it's that the distributed P0, the true data generated distribution, which is an element of some very big model. Under those assumptions we discussed earlier, the average treatment effect can be identified by this estimand here. And then, it's not, you think of this psi px as a mapping of the true distribution into the parameter. This right here is the identifiability part that says, well, I don't, this x might include counterfactual measurements you don't make in practice because it's impossible, but identify it as a function of things I do, the distribution I do observe. That's the psi p0. And in fact, it's on every aspect of the distribution. It can be reduced down to q0. In this case, just the distribution of W and the distribution of Y given A and W. This is the form of the estimand. So it's just the average over W of this difference in predictions when A is 1 and A is 0 for strata W. So it's the definition of the true parameter. Again, Q0, you'll see different notation for this too, and it will get more complicated as the talk goes on, and I apologize because once we start adding cross-validation, it's really hard to keep track of everything. But here is the mean of Y given A and W, this part, and then of course the other part, which is simply the probability of W. And in practice, of course, we use the empirical for that. So we can estimate that non-parametrically with no penalty. So this is just shows the form of it reduced from here, assuming kind of discrete W, but not necessary. And finally, this would be the estimator. You just plug in estimates of Q, so that the regression that you fit, maybe with superlinear here, predict when A is 1 and A is 0 for every W you have in your data set, take the average, and now you have a substitution estimator for your quantity of interest. So this is when targeted learning comes in. I don't know what I feel about this diagram, and always sort of, I mean, it gives you some intuition, but the idea is you have this initial fit, here's the truth, and then you target the estimator, maximizing information in the data towards your parameter of interest. And so you move this initial estimate towards P0, hopefully, and then you use the exact same mapping. So the targeted learning, or TMLE estimator in this case, is just exactly substitution estimator, where we've modified the components of the data generating distribution to optimize estimate of our parameter of interest, and also smooth it so it has a normal asymptotic sampling distribution. We can derive inference from the influence curve, etc. And here is the general algorithm when you have, and again, there's also modifications of this now. There's a lot of research going on in how to implement TMLE, so there's nothing about this that's set in stone at this point, but you might have parameters that involve not just one component of the likelihood where you have to estimate it, so you're not assuming non-parametrics, like the prediction model of y given a and w, but it also might involve another parameter like g, and these kind of clever covariates for the update can contain both, so you have to fluctuate back and forth to estimate them in an iterative fashion. In our case, we're just looking at this one step, something that just it only needs one step in order to derive the estimator. But in general, they can involve iterations across updating these components until they converge. TMLE is double robust and locally efficient. The double robustness is particularly important in things like trials. I mean, I don't think in observational studies you can typically argue you know either of the components that you need to estimate. You don't know their true distributions. So maybe double robust might be a little bit oversold in that case. But it turns out that double robustness indirectly also leads to more just robustness and period. And it's locally efficient. That is, you get them both right. It is the semi-parametric efficient estimator. Very much like or equivalently to the augmented estimating equation approach, the augmented IPTW estimator. So they both operate on the same definition, the influence curve, and they both have the same efficient influence curve. So just to show explicitly how it works in this case, so I can contrast it later, you have initial estimate, which we'll call P(n)(0) in this case. So that could be from superlearner. I'm assuming y in this case is binary, but it doesn't matter. I could be doing this in linear form and just taking the mean. So it's really the mean of y given a and w. And then you augment it, treating this as an offset, the initial fit. And this form of the clever covariate is chosen, so maximizing the likelihood is same as solving efficient score equation. So it becomes a estimator that has the efficient influence curve that you want it to have, that has the properties such an estimator would have. It has this form in this case, just the indicator a is 1 over the probably a is 1 given w, estimated again in some way, like superlinear, minus the other one. And then you just can rephrase it this way right here. I've got this Q bar 1 is the augmented fit, and it just consists of the offset plus a coefficient estimating the entire data set and multiplied by this clever covariate. So it's not necessarily intuitive, the form of it, but it is kind of, look at it, it's kind of, you have some estimate or some way of parameterizing the residual confounding, let's say, or the most efficient way, and therefore you're augmenting the initial estimate by this thing that tends to change the likelihood in the direction of changing the parameter the most. So that's how it's targeted. And you can think of it intuitively that way as getting rid of both smoothing. You're fitting a parametric model that'll smooth the estimator somewhat, and you're adding a bias reduction step, which is like, you can think of it again heuristically as a way of optimally characterizing or parameterizing the residual confounding. Finally, once you get this final updated estimate of the prediction model, you just stick it back in the same way. And that you have your TMLE estimator. Use the influence curve to get the estimate of the standard error, which relies on both GN and QN, and you're good to go. So this becomes the important theory for why you might want to augment this estimator, in that you can, this is the form of linearizing the estimator, where you have the estimator minus the truth can be written as an empirical process. So the Pn star minus P0 multiplied by the efficient influence curve plus some second order remainder. And this is, of course, why we can derive confidence intervals and such, because you can represent the difference between the estimator and the true value as an IID sum of these efficient influence curves in practice. And of course, IID sums are normally distributed, and they'll have the variance of the efficient influence curve over the sample size. Now, in this case, there are constraints on the this DPN, and that is that it has to fall in the so-called P0 Donsker class, which has a specific that's a very general kind of definition. You can come up with specific examples of the types of functions that satisfy it, but in general, and I'm because I'm not really capable of giving great explanations for this, it really means that your estimators for QN and GN can't be too adaptive. If they're too adaptive, you get sort of a dependence in the influence curve within a study, and and therefore the central limit theorem starts breaking down in some sense. So it does have real constraints, and we've seen that in practice. Like you can, depending on sample size and other things, you can overfit these estimates of these aspects of the data generating distribution, and the TMLE estimator starts to fall apart a bit. It gets the wrong inference, it can be biased, etc. So without this additional component I'm going to talk about, you have to think quite a bit about what kind of learners you put in the library if you're fitting something like superlearner. Otherwise, you have the possibility of overfitting based on the violation of this P-concert class, and that condition, also called the interview condition. Really just think of it as adaptiveness of the estimators. And we'd like to create an estimator that doesn't have this condition, so we don't have to worry so much about what goes in the library. It can be more like a machine. Again, I just want to point out, I don't think it's a complete list, but it's a pretty complete list of all studies that have reported relative performance of TMLE estimators relative to other things like, misspecified parametric models, and that's a real trivial one, but also other competing estimators that use machine learning and therefore could in theory be unbiased. And you can see it starts at 2008 when the first paper was out in 2006. Susan Gruber has contributed quite a bit to this work, and her work in collaborative targeted maximum likelihood, showing the practical benefits of using this by simulations. There are some, studies that are relatively neutral, don't have big differences in the performance of TMLE versus competing estimators. Most are pro, and most are also in papers that have to do with highlighting the targeted learning estimation. So, their simulations obviously somewhat designed to show when they're an advantage, but there's also realistic simulations within these, including a couple that I've been involved with. And there's some cons. Those that find the performance to be worse. Now, at one of these studies, it's worse because they fit a parametric. They use a parametric model to simulate, and they use a substitution estimator, which relies on the correct definition of the parametric model. And of course, you're going to get a lower bound. You're going to get better performance because that's a maximum likelihood bound, and these estimators are supposed to be competing in a semi-parametric model. So you can get trivial things where it won't work as well because you've guessed the right model, but I don't think that's terribly important or realistic. All right, now to the CV. What is the difference of the CV-TMLE? I know this is for those that aren't comfortable with notation, it's kind of a notational nightmare, but it really is just a way of, this is in one step, you can explain the entire estimator. So here's the CV estimator. It involves an average over all the validation samples, that's this part here, of the targeted maximum likely estimator, which relies on a global fit of this coefficient on the clever covariate, or you can think just generally using all the data to estimate the augmentation of the original fit, but it's a value. It's the rest of it is only done on the training sample. So your initial fit's only on a training sample. Your augmentation is based on all the data. So you have sort of an independence of the validation sample, and the Q and the G are estimated there, and the validation sample. So it's adding some mechanism to avoid overfitting in that initial step, which means even if I use highly adaptive estimators in the training, the P and 0BN, just at the empirical of one training sample, I evaluate it or to drive the update on the validation sample, which is independent of how it was made, and therefore if it is overfit, it'll perform relatively poorly, and epsilon will be adjusted appropriately to account for that. So, and that's the basic form of it. What you do is you create, let's say you're doing 10-fold cross-validation, you have 10 training samples, you fit the G and the Q, let's say propensity score and the prediction model separately in all those 10 training samples. You use that to define the clever covariate in all the validation samples. You only have to estimate the coefficient on this clever covariate over all the validation samples. But that, because it's a simple parametric model, it doesn't add much overfitting, and then you have now a new augmented one, but it's different for each training sample. So that's why I get the estimator over each training sample, each validation sample, excuse me, and then I have to average them over all of them, and that's my new estimator. It's complex, but you have some intuition of why you do it. What it looks like in specifically for the SMM we're talking about, again, it's just a substitution estimator. It looks like this. That's what it looks like in the TMLE. In our case, it looks like this from above. And what that means is for every validation sample, so when B in IV for the V validation sample equals to 1, you only use those observations to get the estimate of that particular training sample specific estimator, let's say of the average treatment effect. And then you average all those to get your overall estimate. So you get to avoid overfitting, but of course, it's much more efficient than just a single sample split where you could do this because you get to utilize all the data. And here's some heuristics for why it works. Why it gets rid of that Donser class condition, because now you can represent the linearization this way. And here you have a influence function that's really mainly a function of the prediction model and the propensity score estimated on the training sample, but evaluated on the validation sample. So they're much more independent in that sense. And you might expect that it to behave just like an average of IID random variables, which doesn't require these entropy conditions anymore. Of course, always there's a potential for a remainder. And I'm not going to go into much more detail than that, but because of that independence of the Q that's used in the in the influence curve and how it's averaged over in the validation sample and applied, you get rid of this condition. It's shown much more formally in these two papers by Wenjing and Mark, and another one in chapter 7 by same authors in the first targeted learning book. So we would predict that this would maybe perform better, particularly in situations where we are including highly adaptive learners in small sample sizes that may be overfitting. I think one way to think of how this could work in practice is twofold, or how it might help things. One is that if I overfit the original Q to the point where I'm even getting empirical, let's say mean squared error of the prediction model that's less than the true one, then I don't leave any information for the update to have a bias reduction. If I fit them all just right through the data, there'd be nothing left, and there's no way for it to correct any bias in that. That's one way to think of it, of how it works. And also, the same thing I think happens with G, in that you can get these practical violations of propensity score by overly aggressively fitting G in the data, and therefore it goes towards either 0 or 1, and these estimators tend to blow up. So it also sort of accounts for positivity as well. It can ameliorate positivity violations, and in both those ways you might see it improve the estimation. All right, so this is the study. We have these 10 studies that we simulated data based on the data. Again, there's a mix of observational and randomized trials. The interventions are all binary nutritional interventions now, as how we characterize them for simplicity. Lots of different covariates, so the W's are not all the same for every study, depending on what they measured and what's relevant. And what we do is we use a form of simulation based on what's called a parametric bootstrap, introduced by Maya Peterson and Mark and others in 2012. So you basically just use the data, you fit the Q with some very flexible algorithm, you fit the G with some flexible algorithm, you use the empirical for the W, you just randomly draw subjects with a replacement up to the sample size, and then with those fits you can simulate future data sets. And the hope is that if you make these estimates of the data generating distribution flexible enough, you're getting something that's more realistic, and you're able to see maybe pitfalls of certain estimators within the for these data sets. This is the overall structure of it. So you have to estimate these components. We have a continuous outcome, so we're doing something relatively simple. We just add a random normal error to the mean to simulate y, where that error is derived as the variance of y given a and w. Then we simulate the data. We estimate these various competitors, the inverse weighting, augmented, etc. We do this 1,000 times, and now we can look at the performance both of the estimator and the confidence interval. This kind of software that's used, we used this package I talked about earlier, TLVerse, that we're developing as part of this KI project. For the non-CV and CV estimators, we're using SuperLearner, and also the CV-TMLE and non-CV-TMLE, the regular TMLE using these. I want to point out that the original TMLE that Susan wrote the package for has a component of cross-validation built into it. So it also adds more robustness than we're going to show for our TMLE. And then we do compare it to collaborative TMLE. I don't want to go into this too much. We use the discrete version of CTMLE in this case that Susan helped develop and wrote the software for, just because we didn't really spend much time trying to tune it in an intelligent way or try different versions. and it's a very active area of research in our group as well. So, it's been shown to be quite effective in different circumstances. So I think we can not pay too much attention to these results for now because they just add almost a distraction. So the results, here's what you see. This is the mean squared error of this average treatment effect. And you can see some studies, they almost all do poorly. You do see the, in terms of mean squared error, the augmented IPDW estimator does pretty well. It doesn't do that poorly. Sometimes TMLE breaks down, like right here, but of course they all break down in this case, and we'll look more at that in more detail. Sometimes it does okay. I think more interesting is the confidence coverage, where you can see, for instance, this study, TMLE has very poor coverage. Some of these, like the IPTW, the difference between the red line and 1 can be huge in terms of the confidence width, right? Because it doesn't get bigger than 1. So it's a little misleading. It doesn't mean it's good. It could be terrible coverage in that case, just way more than the nominal rate. But you do see pretty consistently good coverage from the CV-TMLE, and sometimes you see a breakdown of the TMLE here. And IPTW, we're using kind of the conservative standard error estimate there, and it often performs very poorly, both in estimation and inference. Here's confidence width. So again, you'll often see CV-TMLE have bigger confidence intervals. That's just to be expected. It's a bigger model. So just from that alone, you would expect it to be bigger. It's also not using all the data in the same pooled way as TMLE. So you would imagine it would lose some efficiency that way, but and that reflected in the width. It's also the width is just biased for TMLE sometimes. So, and the CV-TMLE tends to get standard errors that are more accurate. Again, IPTW often blows up for reasons that have been well established elsewhere. And again, the IPTW, even though it had nominal rates of coverage of 100%, sometimes the confidence interval widths are not that terrible. So it's certainly not a condemnation of that estimator, as it does okay. So summary thus far is both of these appear to be the most robust estimators. Of course, you would expect a version of TMLE and augmented IPTW to be, because they both are based on the efficient influence curve. This should be augmented. So I'm sorry, this TMLE, they perform well on average, but no, that's right. They perform okay. Like when there's no positivity, treatment's randomized, they do better and they perform okay. So it's not like you always have a disaster, of course. AIPTW tends to have overly conservative coverage. So because that conservative confidence interval is much larger, it tends to be conservative. But as I showed, that didn't mean that the confidence coverage was on average much greater than these other ones, et cetera. So one study I want to look at, because it just makes the point, I think, more clearly, is just one of these studies. I'm just comparing the TMLE and the CV-TMLE estimator. Here is the distribution of the estimator itself, and here's the truth. And you can see that CV-TMLE moves it over a little bit towards the true value. More importantly, here's the distribution of the standard errors. So there's just simply bigger standard errors in this case. And you can see the coverage was 0.82 for TMLE and 0.95 for CV-TMLE. So that's a common story. You do definitely gain robustness by that extra step of cross-validation. And this shows, in this particular case, it's really for you really get it because this is a plot of the estimated risk of the prediction model. Either the empirical risk of the TMLE estimator, so overall the data, not using cross-validation, so it'll be an overly optimistic, and that's sort of implicitly used in the construction of the confidence interval. And you have that the CV-TMLE. You can see it's just always greater. So you can see evidence that it was overfit using a large number of flexible learners. And I think I'll just skip this part because we're running out of time and just say that it's a generally good idea to use this added step, I would say, particularly for finite samples, in that it adds a level of robustness that's clear from theory and from practice. This paper, originally written by the MIT group in economics, Newey's involved with, they proposed something very similar, but for estimating equations. The original paper came out, I think, for CV-TMLE in 2010. They do something it's identical theoretically, but 7 years later, and they do it for these estimating equations, because you can do the exact same process for them. They call it double machine learning. I would say otherwise, there's no clear message from these simulations yet. It's good to use this element, additional cross-validation to make the performance better. I didn't show you, but you can also change the definition of parameter, even if CV-TMLE doesn't work. It may be because there's just not enough information in the data to estimate that parameter. You can change the definition by doing something like a realistic rule, or doing both. So again, it's a little bit of a muddled conclusion, but it does, I think, make the point. And I'll just stop there. Thank you.
Thank you very much, Alan. We really appreciate that. There was a lot of information in there. We've got 3 minutes. If anybody has questions, you can type it into the chat window. And while people are sort of thinking of that, I'm going to ask you a question.
Please.
Towards the beginning, you said that if your superlearner library is too data adaptive, then you might end up doing something that would violate this Donsker condition.
Yeah.
CV-TMLE can protect you from that. So my question is, if you're going to use CV-TMLE, do you have to worry about what goes into the superlearner library? And if you're not going to use it, what do you have to avoid putting in the superlearner library? And how can you tell?
That's a great question. So the main message is with CV-TMLE, you don't have to worry that ever extra level of cross validation just means if something's overfit, it will perform poorly and the validation step where you're estimating the clever covariate. It'll be, it'll recognize there's a lot of variance still explained still. So that's that. And I think we've shown that to be reasonably true. It's hard to be over adaptive in CV-TMLE in these things. If you use TMLE, then you do have to worry about it, but not in all circumstances. It's a function of sample size, obviously. Donsker class is a function of sample size. So if the sample size is huge, and so you have and you have lots of replicates, let's say at the same design points, you can be pretty much sure you're not going to overfit no matter what you use. But for finite, for relatively small studies in the thousands, let's say, or the hundreds, it's a real issue because you want to do things that are data adaptive to capture the truth, but you can easily overfit.
Thanks. Then a follow-up to that is when you create those cross-validation folds, particularly for estimating the propensity score, G, how careful are you? Do you do anything special to ensure balance across all the folds?
Balance in terms of what do you mean? But balance in terms of the treatment, or?
Yeah, partly in terms of the treatment as the outcome. Like, is it important for that to be proportionally the same in all the folds?
I mean, that's a good question, and it really is a finite sample versus large sample kind of question. So yes, in finite samples, you can gain a lot of efficiency by making sure you maintain balance, and you can do that. There's a way to do that within, I think, both the superlearner function on CRAN and the SL3 function in TLVerse, that you can specify to keep a certain balance. That's often very important for treatments that are rare or outcomes that are rare. You can do it by outcome too, because you get training samples or validation samples that have so few treatment or so few outcomes, they essentially add no information or they blow up. Mm-hmm. So I didn't talk about that, but it's a super important part of practical estimation of these things.
Okay, thanks very much. Our time is up, so I just want to thank you once again for presenting.